Our final speaker is a student keynote, and so we'll be hearing from Ari Koeppel and from Dartmouth College, who will be talking about standardizing soil thermal inertia derivations with Bayesian statistics.
Right. Hi, everyone. As the last speaker of the morning, I just want to express how grateful I am to the organizers of this conference for bringing together this fantastic group of people. I've really had a lot of fun this week and last week during ESPN as well. So I'm really excited today to introduce or highlight for this community the utility of remotely captured surface temperatures for doing surface process science. I'm going to talk to you about some of the use cases and applications of this type of work. But before I do that, I have to introduce you to some of the historical challenges associated with this work. And then I'll talk about some of the creative solutions that my collaborators and I have been taking to overcome those challenges. So to start, it's worth just going over what this thing called thermal inertia is. It's a material property that we can use to understand and compare materials in thermal space. It basically dictates how a material responds to external energy inputs in terms of temperature. And so if we look at this simple daily surface temperature plot, you can see that high thermal inertia materials are more buffered against change relative to low thermal inertia materials, meaning that their peaks, the amplitudes are smaller, and they're also phase shifted where the peaks are later, they have a lag. An example of a high thermal inertia material would be like asphalt or bedrock. It tends to stay warm through the night. An example of low thermal inertia material would be like loose sand in a sand dune where it gets really hot in the middle of the day, but cold at night. So I also want to give you the explicit definition of thermal inertia. I don't like showing equations in my talks, but when I do have to show them, I like to make it dramatic. This is a Dolly rendering. So thermal inertia, it's the square root of thermal conductivity, specific heat capacity, and density. And that equation will come in handy later. And the utility for understanding surface processes is that we can do near surface geophysics. Specifically, thermal inertia varies as a function of grain size, and I'm showing some empirical evidence of that relationship from some studies in this table. And then it also varies as a function of composition, cementation, porosity, density, soil moisture, and layering, all things that can be really useful to study sedimentary systems. Together, these relationships, as I've said, they allow for geophysical interpretations. And what I think the real utility is that we can do geophysical interpretations over broad regions using satellite or airily derived images. And finally, I just want to point out that thermal inertia is often an important boundary condition in climate models. And I'd argue in this use case, it's actually gone chronically under-constrained. So how do we derive thermal inertia? Well, the lineage of thermophysical analysis has its origins in Mars science, actually. And that's because we're really surface data limited. So we need to use these remote techniques to understand sediments and their properties. We start with a time series of temperature, typically over a day or a year. Here I'm showing a day of Curiosity rover radiometer observations, the black dots. And then we use process-based surface energy balance models to fit those observations. And there's a series of different possible fits for that combination of observations here for various different arrangements of the sediment. It turns out on Mars, this is pretty easy because the atmosphere is really thin and the surface is pretty static. So that model doesn't have a lot of complexity, and that's allowed for a pretty robust mapping of thermal inertia across the entire planet. On Earth, things are a little more complicated. Our atmosphere, as we all know, it's quite dynamic. We have clouds, we have weather, we have moisture. These things make it more complicated. I'm showing you some data here from northern Arizona, which is actually like about as simple as you can get in terms of a surface temperature curve. You can still, this is over the course of 2 days and then some other half days. And you can see that same trend with the hump. But you can also see some subtle relationships like the results of convective heating or convective cooling, and then some scattered clouds. And if we want to invert for thermal inertia in this circumstance, really what we have to do is just take accurate measurements. So we can use a weather station like this to capture all the terms that we need to really dictate a surface energy balance model. And this ultimately serves as the basis for a finite difference model of subsurface heat diffusion, where we model step by step the movement of heat into the subsurface, and then that dictates the temperature at the surface. I haven't actually gotten to the problems, the challenges yet. The challenges isn't here. We can take really accurate measurements. The challenge is that thermal inertia varies non-linearly with some of these properties. Specifically, it varies non-linearly with temperature, and it also varies quite a bit within the range of conditions at our surface with poor fluid content. And so I'm showing this conceptual diagram just to give you an idea of what I mean, which is that as a sediment fills with fluid before it reaches saturation, it goes through a series of regimes in which the moisture that fills the pore spaces actually controls the temperature regulation in different ways. And not only that, but different types of sediment actually have different responses in this way. So we can't just use one curve for all sediment. Clays and sand will have different responses. And so for the utility of thermal inertia, it's worth defining a standard condition. And my collaborators and I have decided that this standard condition should be a dry condition at 300 Kelvin. And then we can model the processes that affect this standard condition, such as soil moisture and temperature. And so here is a plot that I made of relationships for different soil types, ranging from clay to sand over a range of water content conditions. And you can see that those curves vary quite a bit, and that has a strong influence on surface temperature. I'll also point out there's some parameters, specifically M listed in that legend. And that's a variable that we can use to kind of modulate between those different soil properties. So that leads me to my next point, which is that measurement setups and also soil properties site to site have variable influence on how we study surface temperature. And specifically, some of you might be aware of aerodynamic resistance. It's basically this concept that there's like this constant that modulates how air temperature and wind affect heat exchange between the surface and atmosphere. But the aerodynamic resistance with this small weather station versus that large weather station versus reanalysis data, they're all going to be different because you're measuring wind in different places. You're measuring air temperature in different places. And also the surface roughness is different between each of these different sites. And so in that sense, it's actually useful to come up with some terms that we can modify and optimize for in order to integrate data from multiple different sites or even include reanalysis data. And so this is a problem for something like Markov chain Monte Carlo optimization. And we come up with six, in our analysis, we came up with 6 terms that form the basis of this optimization scheme. First is this standardized thermal conductivity. If you remember back to that equation, this is kind of our proxy for thermal inertia. And then that pore connectivity parameter that I mentioned in the soil moisture slide. And this sensible heat coefficient, which is our aerodynamic resistance constant. There's also a latent heat coefficient, which controls how much evaporation affects surface temperature. There's a soil saturation threshold for how soil moisture affects conductivity. And then a soil moisture threshold for the onset of evaporation. And with multiple unknowns, Markov chain Monte Carlo sampling based on Bayesian statistics is great for fitting this type of problem. Essentially, what it does is it works by testing multiple combinations of parameters step by step, and it assesses goodness of fit. Here we use the reduced chi-squared metric. And what you're left with is a probability distribution of the likely value for each parameter. And so here's a result from that site in northern Arizona. We have probability distributions for each of those 6 parameters. We're able to get kind of this median value, which is our best fit, used to fit surface temperature there on the top right. But we're also able to assess a few other useful things, like the uncertainty of those fits based on the breadth of those distributions, and also whether any of these variables are correlated. You can see this line here showing that perhaps there's some wiggle room between those 2 variables. And I just want to mention that we also did quite a bit of ground validation using these heat pulse probes, which have matched the model results. Okay, so this is where I think things get really exciting. So once we've been able to constrain the environmental coefficients, then we can go out and fit for just the thermophysical parameters, basically just thermal inertia over a broader area if we make the assumption that those environmental coefficients apply over that broader area. And we do that, in this case, using aerial thermal images. So these are mosaics, the top 2 on the left and right, mosaics of surface temperature taken with a drone. And now, instead of, like in that Mars diagram, instead of fitting for many, many points throughout the day, now we're just fitting for a few, in this case, 9 over the course of 3 days. And we can use that to derive thermal inertia across this scene. And the value in that is that we can start to see some features that you couldn't otherwise see in visible imagery or even topographic data, such as this striping, this ribbing that you can see in this thermal image and a little bit in the thermal inertia result. And we know from standing on the ground there that reflects this really subtle sorting that's happening on this aeolian sand sheet in northern Arizona. So that work in northern Arizona was this basaltic tephra sand sheet. It was actually part of this broader effort to differentiate volcanic lithologies. And so we did a similar set of work at Kilauea in Hawaii. And we actually found that our initial fits weren't very good there. And it got us thinking. We looked around. We had taken a bunch of pictures in the field, and we noticed that at some of these embankments, there was distinct subsurface layering. So we thought, why don't we add another layer to the model and also have an adjustable depth between those layers? And it turns out when we did that, the model produced a much better result, a much better fit. And it actually matched what we were seeing in the field. So there's this lower thermal inertia on top, higher thermal inertia below it. And what we saw in the field was this really porous, glassy tephra on top from this 1959 eruption, and then this compacted, in some cases welded, lithic tephra in the bottom. Now, if we make that bottom layer ice, then we can apply this to cold regions to study maybe something like I was talking about during our ESPN talk a couple days ago, what happens in a glacial system when the glacier disappears and there's still remnant subsurface ice. Or maybe we can apply this to permafrost settings. Basically, this is again one of many thermal mosaics of that region. We apply a fit. Now we're fitting for depth to ice, and the model produced a thermal inertia, but I'm just showing you depth to ice here because I think that's the interesting result in this case. And we're able to get a sense just based on temperatures and the atmospheric measurements that we took where ice exists in the subsurface. And again, our observations in the field of these little scarps on the side of this lagoon matched what we were seeing with this result. Finally, I want to bring you to this ephemeral channel called Sperry Wash in California, where there is a wide diversity of sediment accumulating in different portions of this channel system. There's a DEM on the left, and that's the thermal inertia result on the right. And one thing that might catch your eye is that really bright strip. That's actually this subsurface flow that's occurring through the channel, which you couldn't necessarily see standing there unless you dug with a trowel. And another exciting thing we were able to do at this site is we collected a bunch of samples across the site and measured their properties, the grain size properties. And we were able to build a machine learning tool that took those properties and took the derived thermal inertia and then made this predictive map of things like roundness and sorting across the entire scene. And it did a pretty good job when we went back to the scene and validated each of these settings. So you could imagine if you wanted to revisit this site and see how this system evolved through time, you could take repeat observations like this and see where the sediment is moving around within this channel without having to go take a bunch of samples year to year. You only have to do that once. And then you can also imagine doing this type of process more regionally with satellite data instead of drone data. So with that, I just want to thank all the contributors to this work. It's been a large team, and I want to point you to the GitHub repo for this model. It also has some pointing to the paper that describes this work in more detail. And I don't know if we have time for questions, but I'm happy to take them. Thank you.
Great talk. We're a little over, so there may be one question, but then you can ask Ari questions at the break. Or you can just catch Ari at the break. Okay.
Can you give us a sense for the physical reason behind the relationship between TI and grain size? Is it something to do with surface to volume ratio?
Yes. So the question was, what's the physical relationship between thermal inertia and grain size? It primarily actually has to do with pore space. So the limiting factor is how heat is transferred between grains. If there's a lot of contact area between grains, it can transfer much more easily. If the contact area is very limited, it has to transfer through the fluid that fills the pore space, and that's much more limiting.
And